Today's notes are all about limiting reactants and percentage yield. So we're going to be learning about different reactions and how different reactants in them can limit how much product is produced. And then once we've talked about product being produced, we're going to learn about percentage yield, which helps us determine how much product was produced as opposed to how much should have been produced by our reaction. Our objectives aligned with this are to identify the limiting reactant in a reaction, to calculate the amount of excess reactant that would be left over after a reaction takes place, and then to calculate percentage yield for a reaction. So far, as we learned stoichiometry, we've been looking at ideal reactions, where everything gets used up completely every time. We have exactly as much as we need. This is not what happens in the real world. In laboratories, we often have way more of one reactant than we need than another. In this case, that means one of those reactants is going to get used up before the other one does, and we call that one the limiting reactant. It's the reactant that limits the amount of the other reactant that can combine with it, and therefore limits the amount of product that you can form in the chemical reaction. Consider this reaction between carbon and oxygen. If we take solid carbon and we combine it with oxygen gas, we can produce carbon dioxide gas. If we look at the equation they gave us, we can see that it takes 1 mole of carbon to react with 1 mole of oxygen to produce 1 mole of carbon dioxide. So based on that, if I then told you I'm giving you 5 moles of carbon and 10 moles of oxygen, mix them together, which one of those is going to get used up first? Well, in this case, it's very easy to tell because this is a very simple equation, and I've given you the number in moles. So we can tell, obviously, that if it's 1-to-1, the carbon is going to get used up first, which means it is going to limit the amount of carbon dioxide that can be produced and is therefore the limiting reactant. Sometimes you'll hear people use the word limiting reagent. Same thing. So, how do we determine which is a limiting reactant? Because it's not always going to be as easy and face value as that example was. While it may not be as straightforward and visually easy to solve for, finding the limiting reactant is really not that difficult. Okay, you're going to take your starting materials and convert into moles of product. If your starting materials aren't in moles already, you will need to convert them to moles. If your equation that they give you for the reaction is not balanced, you'll need to balance the equation. But then once you have a balanced equation and starting amounts in moles, it's very easy to use stoichiometry to calculate how many of each reactant, how many moles of product it's going to produce. Whichever reactant then produces less product would be considered the limiting reactant. And there's another way around this too. You can also just take reactant A and figure out how many moles of reactant B would be needed to react with it. And from there, you can determine, well, do I have that many moles of reactant B? Because if I have that many, then, or if I have more than that, then A is the limiting reactant. But if I don't have that many moles of B, then B is my limiting reactant. This all sounds a little abstract, I'm sure, so we're going to run some example problems so that your brains can wrap around it. Okay, so we're looking at calcium hydroxide. It's a base. It's used to neutralize acid spills. We pour it on top of them. And it reacts with hydrochloric acid in this equation to produce calcium chloride and water. If I spill 6.3 moles of hydrochloric acid on the floor, and then I put 2.8 moles of calcium hydroxide on top of it, which one of these substances is the limiting reactant? Am I going to have way more calcium hydroxide than I need? Did I just waste calcium hydroxide? Or did I not put enough on this and there's definitely still hydrochloric acid just sitting in that puddle? Well, here is how we would run it. we're going to pick one of the reactants and determine how many moles of the other reactant would be needed to react with it. You can pick whichever one you want. There is not a right or wrong to start with. I am going to pick calcium hydroxide. So if I'm looking at my equation there, you can see that there is 1 mole of calcium hydroxide to 2 moles of hydrochloric acid. So let's start with my 2.8 moles of calcium hydroxide that they told me I had. That's how much I put on the pile. And I'm going to take this times that mole ratio. So remember we said it's 2 moles of hydrochloric acid for every 1 mole of calcium hydroxide. So moles of calcium hydroxide cancel, and I'm left with 5.6 moles of hydrochloric acid. So if I had 5.6 moles of hydrochloric acid, that would use up the entirety of these moles of calcium hydroxide. And when I look at my equation, at the problem, they told me I started with 6.3 moles of hydrochloric acid, which means I have more hydrochloric acid than I need to react with the amount of calcium hydroxide I have, which makes calcium hydroxide the limiting reactant. This is my limiting reactant. Okay? Thought I had a button here to just wipe the text, but I guess I don't, so I'll scribble it away. There we go. Don't worry, we're running another example problem, okay? There's black oxide of iron, which is written Fe3O4, and it occurs in nature as the mineral magnetite. But you can also make it in a lab. You do this by a reaction between red-hot iron and steam, and it follows this equation. So you're going to take iron in its solid form, it's going to be red hot. You're going to react it with water in its gas form, it's steam, and you're going to wind up with magnetite, or black oxide of iron, and hydrogen gas. So if I do this reaction with my 36 grams of water and 67 grams of iron, which one of those is going to be my limiting reactant? This problem is a little bit longer, okay, so bear with me as we go through it, because first things first, we have to convert those starting amounts in grams into moles if we're going to make this work. And then once we've converted them to moles, we need to figure out how much product they're going to make. And we want to pick the same product. So I'm going to set this up and I'm going to run multiple steps at once. I will try to be as clear as possible. Okay, so let's start with the iron. They told us we had 67 grams of iron. And I want that in moles. I really cannot draw an E to save my life with this pen. There we go. So we know that for every 1 mole of iron, we have 55.85 grams of iron. So grams of iron cancel. And then instead of getting my product here, which would be I could just go and have moles of iron here. But instead of doing that, I'm going to not make this a super long process. And instead, I'm going to go straight into what I want to find out, which is I want to know moles of one of the products, because that's how we're going to determine which one of these is the limiting reactant. So I'm going to say, let's do the magnetite, the black iron, whatever it's called. Okay, so we got to look back at that equation. We got to compare. See, we start with 3 moles of iron, right? For every 1 mole of Fe3O4. So when I run this, then moles of iron cancel as well, and we're left with moles of product. And when I do the math, it comes out to be 0.400 moles. Now I'm just going to repeat this process with the other reactant. I'm going to do the exact same thing. I'm going to convert it into moles of that substance and then into moles of Fe3O4. So I can see which one of these would produce more if it got completely used up. So we started with 36.0 grams of hydrogen, or not hydrogen, water. Okay. So then I need the molar mass of water because I've got 1 mole of H2O for every 18.02 grams of H2O. And then again, I don't want to stop at H2O. I want to move on to moles of Fe3O4. So I'm going to look back at that equation, and for every 1 mole of Fe3O4, there are actually 4 moles of water. So again, moles of H2O cancel, grams of H2O cancel, and I am left, when I do this math, with moles of Fe3O4. And when I do the math, I find that it is 0.499 moles. So because of that, I can confidently say that iron, my top one here, this is my limiting reactant, because there is less. We make less product with this one, which means we're going to run out of this one before we run out of this one. So this is our limiting reactant. Now let's talk, what is the mass in grams of black iron oxide that is produced? Okay, we can answer that question. We've just got to go and convert from moles to grams. That's an easy conversion. We've done that before. So how do I know the moles? Well, it would be the moles produced by the limiting reactant. So we just saw that at the end of our last equation. If we have iron as the limiting reactant, then that means we are at max making 0.400 moles of Fe3O4. So then we just have to go out and calculate the molar mass of Fe3O4, which just so happens to be 231.55 grams of Fe3O4 for every 1 mole. It's a big molar mass. Makes sense. Got a lot of heavy atoms in it. So then moles cancel, and we are left with 92.6 grams of Fe3O4. So there it is. That's how much we would make. And then what mass in grams of excess reactant remains when the reaction is complete? So we want to know when we're finished, how many grams are we going to have? This requires a few more steps. So we have to figure out first, what's the mass in grams of excess reactant that gets used in the reaction, and then we can solve for what amount would be left over. So if we have I get my pen back, 0.400 moles of iron, then how many moles of this H2O, that's not our limiting reactant, how many moles of it would be used up? So we got to go back to that mole ratio that we had before. 4 moles of H2O for every 1 mole of iron oxide. And then we're going to want to convert that to grams. So we know that for every 1 mole of water, our molar mass is 18.02 grams of water. And that winds us up with approximately 28.8 grams of water that gets used up. This is used. They want to know remains. They want to know left over. So then it's just a simple subtraction problem. We know we started with 36.0 grams of H2O, and we're just going to subtract 28.8 grams of H2O to find out that we are going to be left with 7.2 grams of H2O. That's our leftovers. All right. Now let's talk percent yield. The stoichiometry problems we do in class are theoretical. So what we're calculating is a theoretical yield, which means if everything goes the way it's supposed to go, this is how much we will end up with. Okay? It's the maximum amount of product that you can produce given your starting reactants. But in the lab, just like we don't always use exact amounts of each substance, we also very rarely get the maximum amount that we are supposed to. And there's a number of reasons why. Okay, there's things like side products being produced that we didn't expect, or impure reactants to begin with. There's lots of different reasons, but what happens is there's an actual yield, which is when you do this and then you weigh out how much product you actually received. That's your actual yield. And to compare theoretical yield and actual yield, we use something called, I don't know why that says theoretical yield there, it should say percent yield. Okay? Percent yield, again, not theoretical, but percent yield can be calculated using this formula. Take your actual yield, so your weighed amount that you measured in your lab, divide it by your theoretical yield, and then multiply that times 100 to get yourself a percentage. Pretty straightforward. Here's our practice problem. Dichlorine monoxide, which is Cl2O, is sometimes used as a powerful chlorinating agent. It can be produced by passing chlorine gas over heated mercury 2 oxide using this equation. What is the percentage yield if the quantity of reactants is sufficient to produce 0.86 grams of chlorine but it only produces 7.71 grams. So we just have to run the equation from the previous page. Okay, we're going to take that actual yield, our lovely 0.71 grams, and we're going to divide it by the theoretical yield, which was 0.86 grams. The grams are going to cancel because we're going to get a percentage here. This is a ratio. Okay? So we're going to wind up with 0.83 and a bunch of numbers afterwards, which when we take it times 100 will give us an 83% yield. So not terrible, not great. We'd like to see a higher yield, but not terrible. All right, that should be the end of the notes for today.